Good morning. I appreciate you, I appreciate being asked to speak here this morning. I'm going to be talking about potential effects of predicted climate change on biological communities in Arkansas. I'm sorry. Well, I'm not a climatologist. I'm a hydrologist slash aquatic biologist. So the climate slides, well, USGS does have a climate change group. It's one of our mission areas, so I got these slides from Virginia Burkett, who's the chief scientist for our global climate change research. So here's where this talk is headed. I'm going to start talking about, recent climate or recent weather. Start out maybe going back couple of years, and then go back maybe something close to 100, and then I'm going to shift gears and talk a little bit about the climate models, and then finish up by talking about potential effects of climate change on hydrology and biology. So for sure, there's strong consensus in the climate change community that there's uncertainty there. There's uncertainty in all modeling efforts, and as you go, just like Ed said this morning, your meteorologist can tell you pretty good what's going to happen this afternoon, but maybe next week is a little bit more uncertain, and then you go out to next month. It's probably going to be warmer than it is today, but beyond that, you can't be very specific. And then as we go from a global results, looking at the results of climate change models globally, and then you shift down to Arkansas, well, then that uncertainty really increases. And the other thing is that there are going to be some surprises down the road. We don't really know. We've got some good ideas, but it's difficult to predict with exactly what's going to happen. And so there's going to be some things that surprise us about climate in the future, I'm sure. And then how does that climate affect ecosystems? There's going to be some surprises there too. So we talk about recent climate. We're just coming out of, well, I don't know if we're coming out of a drought or not. I guess that remains to be seen. But the last summer, fall, and the summer before that were certainly dry years. Farmers would tell us that it was a drought. We don't need any scientists to tell us that. But then you go back another 2 or 3 years, and we certainly have had some high flow, some flood episodes. Now let's look back maybe about the last 30 years. So this map shows, this is the number, the change in the number of winter freezing days in the southeastern United States. And so here's Arkansas. And so you can see that typically, a good part of Arkansas, we saw a change of maybe 3 to 5 days decrease in the number of freezing days. So that's some indication that we're seeing some climate change, at least in the short term. This is some temperature data from Eureka Springs up in the northwestern part of the state. And, I don't know if looks like there might be an upward trend there. There's a lot of variability from one year to the next. That's the way that it is. But that makes it a little bit more difficult to decide if there really is a trend. And it looks like maybe there is. It's the same sort of data, Eureka Springs. We're looking at the monthly minimums average for the year, and I just dropped a line through there to kind of smooth out the data. It's just by sight, really. But it looks like it's going up, and then it decreases here, and in the 50s, and then increased again. Now, if we look at precipitation trends over the last, approximately 100 years, 110 years, the thing I want to point out here is that in Arkansas, you've got different patterns if you look at it seasonally. So if you look in the spring, we're tending to see maybe a 20% decrease in the northwestern part of the state. You get down to the southern part of the state, and it's maybe no trend at all. We go to the summer, and we're seeing, which is, you know, that's the main agriculture period, growing period, and we're seeing decreases of maybe 20% or so. You get into the fall, down here, we get with the different colors. That blue is we're looking at increases in precipitation. Winter is maybe slight increases as well. So that's over the last 110 years or so. Now we're going to jump here into looking at the climate models. There are, you know, probably in the range of 25, you know, widely accepted models out there looking at climate change, and these are three of them. Really, what I want to point out here. Okay, so this is, if you look horizontally, this is related to one particular model. This is another model, and then a third one, and then this is what the model predicts for the 2020 to 2030 period, basically, and then this is the 2090 to 2100. So what I want to show here is kind of get an idea of, or I want to get across the idea to you of uncertainty in these models. And so to do that, if we look at this light brown is the 2020 to 2029 period, and the darker blue, I guess, is the 2090 to 2099. So looking at the plot, this is if you go in this direction, the horizontal, that's the global average surface temperature change in degrees Celsius. If you take like a 5 degrees Celsius, that's about 10 degrees Fahrenheit. You can just double the numbers there to get, if you want to go to Fahrenheit. And then in the vertical direction is your uncertainty. So if we look at this model, our group of models, you see that out of the 2090, 2099, you've got higher temperatures are expected than they are in the 2020 to 2029 period. I'm just getting tired of saying that. But you're uncertain, well, your relative probability is higher in the short term. That goes back to our weatherman saying that it's going to rain tomorrow, but not knowing so much what's going to happen 2 months down the road. And then if you look at the three models, in the short term, they're all predicting about the same thing, an increase in the northern hemisphere of maybe about 2 degrees Celsius. And that's pretty consistent, even, you know, on a geographic basis. These three maps look fairly similar. You jump out here to the end of the century, and the colors are a lot different. So the three models are actually predicting quite a bit of difference between them. So, but temperatures they're all predicting higher temperatures. Okay, I'm going to save a little time, jump through this one. Okay, now here we're looking at temperature changes, 3 different time periods, near term, short term, or near term, kind of middle of the century, and then the last 30 years of the century. In northern Arkansas, this particular model is predicting an increase of about 3 to 4 degrees Fahrenheit. And down in the southern part of the state, where we've got more of the, well, I don't know, the southern part of the state, 2 to 3 degrees Fahrenheit. Then you jump over here to 2040 to 2069, a 7 to 9 degree Fahrenheit increase by the end of the century. So that's, I mean, even that's a lot. And then here you get to the end of the century, 2070 to 2099, 10 to 11 degrees, 9 to 10 degrees Fahrenheit in the southern part. That's really a lot. You just imagine that instead of having our 100-degree temperatures in the summer, we've got 110. All right, so same sort of map. Here we're looking at precipitation. In kind of the short term, we're looking at not much change, maybe plus or minus 2%, depending on what part of the state you're in. Now, if you jump into 2040 to 2069, it's maybe a 6 to 8% decrease in the southern part of the state, and ranging up to maybe, 2 to 4, 0 to 2% decreases up in the northern part of the state. But pretty much the whole state is going to see 5 to 10%, well, 5 to 6 or 8% decrease in precipitation. And then you get to the end of the century, and we're seeing, I think that actually says 16 to 18% decreases through the southern part, 12 to 14, 4 to 6% decreases in precipitation. So, you know, there's uncertainty there in the models. There's uncertainty in terms of, well, how are we going to manage that? How are we going to respond to those higher temperatures and in some cases lower precipitation? And then the reason I said sometimes lower precipitation is because if you look at a seasonal basis, we're seeing different patterns. Here in December to February, it might actually be an increase we're seeing. So more precipitation in the wintertime. We get into March, May, you know, it's maybe plus or minus 5%. But then we get into the real heart of the growing season, June through August, the hottest time of the year. We're, you know, in addition to being hotter, we're seeing decreases of 5 to 10% maybe. That's what the model's saying in precipitation. Then we get into September, November, where we're again maybe more of an increase in precip. So season of the year matters too. The Arkansas Governor's Panel did put out a report on climate change. That's available on the web. If you just Google, you'll find it. Now I want to talk about how does this, you know, if we do see these increases in temperature and on an annual basis decreases in precipitation, what does that mean to hydrology? What does that mean for biological effects? Well, you know, from a hydrology standpoint, that means we've got to start planning for something different than what we're seeing right now. And Ed covered that 2 or 3 times today. Now, one of the things hydrologists are starting to talk about is something called stationarity is dead. Well, what I mean by that is that, okay, here's some data. This is annual stream flow plotted by year at a site up on the 11-Point River. Well, okay, so somewhere in there is the average. If we plan on that data, if we use that to make our planning decisions, we might be missing the boat depending on what kind of changes we see. So if this is some hypothetical data out here. So maybe say this is out, I put 2010, maybe this should say 2050 or something. So if that mean from that earlier period, if we're using that to make plans for the future, and then in the future where our mean stream flow is much lower, we haven't been using the right numbers to plan. The problem is we don't know exactly what this number is, what this new mean is going to be. So I guess that you kind of get into some risk assessment stuff there, but you know, you've got to keep collecting data, and you've got to be aware that maybe the old data is not as applicable as you'd like it to be. I think I'll just skip over that. So potential hydrologic effects. We think that there's probably going to be increased evapotranspiration. That's important, you know, to the agricultural community certainly, but it has effects on streams as well. We're probably going to see increased water temperature, decreased recharge of groundwater, decreased discharge of groundwater into surface water, decreased annual stream flow. But we might see actually more variability in rainfall. We might see more precipitation during sometimes the year, so we got higher floods, more erosion maybe, and so water quality changes going on there. And we might see some seasonal changes as well. Now, this has potential hydrologic and social effects. Now, the southeastern part of the United States has really been blessed with fairly abundant water, certainly compared to the western United States. But if we've got less water, it suddenly becomes more valuable even than it even is at the present time. And there's going to be increased competition for water. You know, that just makes sense. If you've got less of it, more people, more hotter temperatures, less precipitation, it's going to become more valuable, and then leading to increased competition. So if we now look to how it's going to have an effect on plant communities, agricultural crops would fall in that same category. I mean, we talk about the same sort of thing. If we've got higher temperatures, In some cases, certainly on an annual basis, we're probably looking at decreased precipitation, increased evapotranspiration. Then that's going to decrease soil moisture, can cause increases in fire, and then soil moisture itself can cause changes in the plant community. And fire can have a secondary effect on plant communities. Now, if we're talking about springs, you know, the northern part of the state particularly, you've got a lot of springs up in that karst area. In some of those springs, you've got sensitive species. You've got the same increases in temperature, lower rainfall, more evapotranspiration. That's going to give you higher water temperatures, probably less groundwater recharge, less spring flow. And so that, you can see where that could have an effect on spring communities. We don't know a lot about what that actually means. I'm just kind of talking here conceptually here. Now if we look at streams and lakes, if we got less stream flow, warmer water temperatures, less reaeration, less capacity for assimilation of organic material, less that dilution is a solution for pollution. You see that, you know, one of the things you might see is lower dissolved oxygen concentrations. And that, you know, we can then see some declines or elimination of sensitive species. There's a lot of things that can happen here. We don't know, you know, with a lot of certainty about what that is. With birds, the winter range of the Audubon Society says 58% of the continental birds have shifted their ranges northward over the last 40 years. And there's 95 species in Arkansas. You know, cardinal is one that they say has moved north about 190 miles. Now, how much of that is, you know, climate change, or how much of it is, you know, proliferation of backyard feeders? We don't know. But again, that's kind of a confounding factor, so that, and which goes back and applies to some of the other things I've been talking about, like with the springs and streams and lakes. We don't always know, you know, it's difficult to separate out some of those different factors that are coming into play there. How much of that is strictly climate, how much of it is other things that are going on. And so it takes some data collection to sort all that out. With amphibians, you know, you've got warmer temperatures that could lead to earlier breeding. You know, a lot of those do their breeding. You know, the spring peepers and everything, you know, which should be coming on here any time now. Get a few warm days. So, with warmer days, we could get some earlier breeding. But then, if you have a cold day comes in, and you have a cold snap, that could cause some problems. And then, if you've got less water in the spring, maybe you've got you've got drying effects. So just to summarize, you know, there are uncertainties there. We've got uncertainty in the models. Then once you've got the model calibrated, you've got uncertainty in, like, what do I want to say what do I want to use for my simulation? I've got a model calibrated. Do I want to say that we're going to keep putting out greenhouse gases at the same rate we are for the next 50 years, or do we want to say, okay, let's say we drop it by 10%, or maybe it goes up by 10%. So, you know, which one of those scenarios is actually going to play out? Is the model accurate in the first place? The data that we're using, there's some uncertainties there. And then how's that going to affect the biology? There's uncertainties there. So I think there's a lot of uncertainty out there, but that doesn't mean that we don't have some good information at the same time. But the climate models in general are predicting increases in temperature, particularly out, you know, towards the end of the century. Their climate models are predicting, you know, there's more variability in the precipitation, particularly if you're looking at a seasonal basis. But just in general, kind of conceptually, you know, these warmer temperatures, maybe more variable and lower precipitation during some critical times of the year, those are likely to have widespread biological effects.